This is your presenter Asloob Mudassar, and I am presenting slide number 56 of the course on laser physics. Question is, derive expressions for transition cross sections, gain and absorption coefficients for the case of degenerate levels. Answer is, considering a two-level system in which level 1 consists of G1 sub-levels and level 2 consists of G2 sub-levels. The sub-levels are degenerate, that is, have the same energy or are strongly coupled. Let us define N1 and N2 as the total population of levels 1 and 2 respectively at any time t, and N1i and N2j are the populations of the ith and jth sub-levels of level 1 and level 2 respectively. Under thermal equilibrium, the population of each sub-levels of level 2 and level 1 will obey Boltzmann relationship given in equation number 56.1, that is N2j at equilibrium. The superscript E stands for equilibrium. N2j at equilibrium is equal to N1i at equilibrium multiplied by e to the power minus E2 minus E1 over kT, where E2 is the energy of the jth level of level 2 and E1 is the energy of the ith level of level 1. Sub-levels of level 1 and level 2 being in thermal equilibrium and being degenerate have the populations given by, that is, the population of N1i at equilibrium is equal to N1 at equilibrium divided by G1, that is, the N1e divided by G1 means that the total population of the N1 level divided by the number of levels present in that level. And similarly, we can write N2j at equilibrium is equal to N2e divided by G2, that is the total population in level 2 divided by the total number of sub-levels in that level will give you the population of any level, any sub-level, which we here call jth level. So N2j is equal to N2e over G2. So we have written the populations of the sub-levels, that is N1i shown in red and N2j shown in blue. So we can write this equation, that is equation number 56.1 can be rewritten with the help of these two populations, that is N1i and N2j in terms of equation number 2. So we have N2 at equilibrium is equal to 1 N1 at equilibrium multiplied by the ratios of degeneracies, that is the G2 over G1 and multiplied by e to the power minus E2 minus E1 over kT. So now we have written the expressions in terms of the overall populations of the level 2 and level 1. Let an electromagnetic wave passes through the material. The rate of change of the overall populations N2 due to all radiative and non-radiative transitions between the sub-levels J and I is given by. So here we are writing down the rate of change of overall population N2 is given by as shown in equation number 3, that is dN2 over dt is equal to minus. We have used two summations over here. One summations will have a maximum value equal to G1, the other summations, that is the summation over G over J, will have a maximum value equal to G2, because G1 and G2 are the number of levels present in the number of sub-levels present in level 1 and level 2 respectively. And the index I stands for the sub-levels in level 1 and the index J represents sub-levels in level 2. And you see that here we have represented within the square bracket 3 processes, that is Wji is actually the transition rate for the stimulated emission from the level J to the level I multiplied by the population in that level, in the jth level. So we have Wji multiplied by N2J, and you see that there is a negative sign outside this square bracket, so this term is negative. It means that due to stimulated emission, the population of N2 will decrease. Now the negative sign outside this one will multiplied by the negative sign of the second term, and that term becomes positive. And we have Wij, which is the transition from level I to J, that is the absorption transition from the sub-level I to the sub-level J, and N1 is actually the population in the ith level. So we have written this one, and you see that this is the absorption term. So since this will carry an overall of a positive sign, which means that the population of the level N2 will increase. So the first term due to stimulated emission will decrease the population of N2, whereas the second term will increase the population of N2 because of the absorption. Now let's consider the third term, which is N2J over tau Ji. Tau Ji is actually the spontaneous lifetime for the level J to level I. That is the particles which will decay from the level J to level I, that will have a lifetime which is given by the spontaneous lifetime tau Ji. So this will decrease again, it will have a negative sign, so it will decrease the population of the level of N2. So the population of N2 will decrease with the third term, which is the spontaneous emission term. And 1 over tau Ji will give you the rate of spontaneous decay. And since we are talking about the spontaneous decay from level J to level I, so we have the population in the numerator as N2J. So I have explained these three terms, and you know that I have written only for the population from level J to level I, but you see that here we have sum over all possible levels, all possible J levels and all possible I levels, which go from J is equal to 1 to G2, and the other sub levels in the level 1 will go from I is equal to 1 to G1. So we have summation over all the possible sub levels present in level 1 and level 2, where Wji is the rate of stimulated transition between J and I sub-levels, and Wij is the rate of absorption or the rate of stimulated absorption from sub-level I to level J, and 1 over tau Ji is the rate of spontaneous decay, including both radiative and non-radiative decays. So you see that here the spontaneous emission will include both of these radiative and non-radiative decays. Transition rate and the electric dipole moment have been defined earlier in one of the previous slides, which we have reproduced over here. So capital W is equal to, which is the transition rate written in general expression, capital W is equal to 2 pi square over 3 n square epsilon naught into h square, and in the numerator we are multiplying with the absolute square of mu multiplied by the rho multiplied by the function gt of nu minus nu naught, and then we have the mu to 1, which is the electric dipole moment for the transition from level 2 to level 1, is given by the integral in mu 2 star er into u1 and dv. Integration is with respect to dv, volume element, and you see that u2 is actually the special part of the wave function corresponding to level 2, and u1 is the special part of the wave function corresponding to level 1. R is the radius of the electron from the nucleus, and u2 star means that we are talking about the complex conjugate of u2 wave function. And these two functions, that is the W and mu to 1, have already been defined in some of the previous slides. Okay. Now we can write, looking at the expression of W, we can write the Wji and Wij following the relationship given over here at the end of this slide, that is W, capital W, we can write the other two W's as Wij is equal to this expression. You see that we have written the reverse indices at the mu. So Wij and contains mu ji, and similarly Wji contains mu ij, and the rest of the quantities are the same. And this mu ij is equal to integral of, as defined, mu j mu j star u j star ui and dv. And similarly we have mu ji defined by the integral with mu I star with u. This is not mu, this is u I star uj and dv. So we have defined mu ij and mu ji, but these two mu are equal, and we can say that the absolute square of mu ji is equal to absolute square of mu ij. The proof is given over here. For example, absolute square of mu ji can be written as mu ji multiplied by mu ji star. And then you know that the red term can be written as with the change of indices, that is mu ij, but you see that we can take the complex conjugate of this quantity. And similarly the blue term can be written without the complex conjugate, but reversing the positions of the indices. And then you see that at the end we have mu ij, the second last expression on the right, mu ij multiplied by mu ij star, and this will give you the absolute square of mu ij. So you see that the absolute square of mu ij is equal to absolute square of mu ij. You see that when these two mu's are equal, that is their absolute values are equal, then of course the rest of the parameters are the same on the right hand side of both Wij and Wji. So it means that Wij and Wji are equal. That's why we have written over here Wji is equal to Wij. All sublevels within each level will be equally populated, provided quick relaxation occurs between the sublevels to ensure thermal equilibrium. So this is a very important condition. And in practical lasers this condition is ensured. Under such a scenario we can write. Now you see that we can writing down the population of the ith level, which corresponds to the level which is the sub level in level number 1. So we have written the n1i is equal to n1, that is the total population present in the level 1 divided by g1, number of sub levels. So the population of the ith level of the general level of the general sub level in the level 1, which we designate as I, is population of that is population n1i is equal to n1 divided by g1. And similarly for a general level j in level number 2, the population of that level can be given as n2j is equal to n2 divided by g2. n2 is the total population in level 2 divided by the total number of sub levels there. So we have written n1i and n2j. Now you see that we can, okay, now introducing these simplifications, we can write equation 56.3 as this is the equation 56.3, and you see that now we are going to plug in the values of n2j and n1i on the right hand side in equation number 56.3, and under that condition we get equation number 4, which is given over here. dn2 over dt is equal to minus w, because since w is the same, wji is equal to wij, so we can take the w common outside, so we have a minus w, within the parenthesis we have n2 over g2 minus n1 over g1 and minus n2 over tau. And in this equation w is given by w is equal to 2 summations 1 over I is equal to 1 to G1 and the other over J from J is equal to 1 to G2, and then W of Ij, or this is also equal to W or some two summations and W of Ji, because we have proved that J1 W of Ji is equal to W of Ij. So these two quantities are equal, that is the two summations are equal, and we have set them equal to W. That's why we have introduced W in equation number 4. And we have introduced 1 over tau over here. This 1 over tau, which is present in equation number 56.4, we have introduced 1 over tau is equal to summation over I is equal to 1 to G1, and summation over J is equal to 1 to G2, and 1 over tau Ji divided by G2. We have written this quantity is equal to 1 over tau. So that's why we have written the simplified version of equation number 3 as shown in equation number 4 by introducing capital W as given over here and 1 over tau as explained. We can identify Wn2 over G2. You see that here we have W and 2 over G2, and similarly if we multiply W inside, we have W into N1 over G1. So let's understand what these terms are. We can identify Wn2 over G2 as the rate of change of the total upper state population due to all stimulated emission processes. You see that W is again a rate of change, but you know that here Wn2 over G2 will give you the rate of change of the total upper state population due to all stimulated emission processes, and Wn1 over G1 as the rate of change of total lower state population due to all absorption processes. To identify the terms on the right hand side in equation number 4, that is over here, we describe the change in photon flux dF when a beam travels a distance dz in a material in the following way. You see that we have already talked about the change of flux when an electromagnetic wave passes through a material having material of thickness dz. You can look at one of the previous slides. Here we are producing that dF, the expression that will give you the change of photon flux dF is equal to W. Within parentheses we have N2 over G2 minus N1 over G1 multiplied by dz outside the parentheses as shown in equation number 5. So it means that we can introduce dF in the above expression. Okay, thus the stimulated emission cross section sigma 21, this is the sigma 21 is actually the stimulated emission cross section, and the absorption cross section denoted by sigma 12 can be defined as, this is by definition, that is sigma 21 is equal to W over G2 into F, and sigma 12 is equal to W over G1 into F. So these are the definitions of the cross sections. The red one is the cross section for the stimulated emission process, and sigma 12 written in blue is the absorption cross section. So if we can, you see that W over F is common in both these expressions. If we eliminate W over F from these two, we can get G2 into sigma 21 is equal to G1 into sigma 12. Thus we can rewrite equation 56.5, that is this equation can be rewritten as when N1 over G1 is greater than N2 over G2. We can write N1 over G1 on the left of the parenthesis and N2 over G2 on the right side as shown over here. So we have dF is equal to minus W, and within the parenthesis we have N1 over G1 minus N2 over G2 multiplied by dZ. And we can take some factors common over here, and we can write minus W over G1F, because we want to introduce some important parameters over here. The rest of the quantities within the parenthesis is N1 minus G1 over G2 into N2. and we have on the right hand side f into dz, because we have multiplied by capital F over with to the dz, and we have also divided by capital F to the w. So w over g1 f, this f has been compensated by multiplication in the numerator, and you know that w over g1 f can be introduced, can be replaced by sigma 1 2. So we are introducing sigma 1 2 over here, and this term in the parenthesis can be represented by the f this is sigma 1 2, and the term in the parenthesis, these two terms sigma 1 2 and the terms in the parenthesis can be combined in the form of alpha. So we have a minus alpha into capital F into dz. What is this alpha? This alpha is defined over here. Alpha is equal to sigma 1 2. Within the parenthesis we have n1 minus g1 over g2 multiplied by n2. This is actually the absorption coefficient, because we are assuming that n1 over g1 is greater than n2 over g2. So here we have introduced sigma 1 2 as the absorption coefficient. That is, alpha is the sigma is actually the cross section and alpha is actually the absorption coefficient. Now in the other case, if we assume that n2 over g2 is greater than n over g1, we can rewrite equation this one, that is the equation number 5, following the style as given over here. We can write df as sigma 21 by introducing the term over here. Sigma 21 is equal to w over g2 f. Introducing this one, we have df is equal to sigma 21 multiplied within the parenthesis we have n2 minus g2 over g1 into n1, and then on the right hand side we have f into dz. So the term sigma and the term within the parenthesis can be written together by the symbol, can be replaced with the factor by the symbol g. So we have g into f into dz, where g is equal to sigma 21 multiplied within the parenthesis we have n2 minus g2 over g1 multiplied by n1. So this term will be referred to as the gain coefficient. So alpha is actually the absorption coefficient and over g is actually the gain coefficient. So you see that we have evaluated all the expressions that was required in our question over here. Derive expressions for the transition cross sections, which we have done. We have derived the expressions for the cross sections, and the gain and absorption coefficient. We have also derived expressions for the gain coefficient and the absorption coefficient, which has been represented by small g and alpha in our expressions. For the case of degenerate levels, because the levels have the degeneracy g1 and g2 for the level 1 and level 2. So all the necessary expressions have been derived in this slide number 56. So this is the end of slide number 56.